Welcome to the video on proofs by mathematical induction, contradiction, and counterexample. First, we'll learn about proofs by mathematical induction. So for this form of proof, you start by proving the basis case. So the initial one where n equals 1. And then you'll prove the induction. So to do this, you assume that the statement is true when n equals k, and then you show that it's true when n equals k plus 1. So you'll plug in k, and you'll plug in k plus 1 and show that it's true. And this will make more sense as we do an example. So here we have our first practice problem. It says, using mathematical induction, prove that 2 times 2 to the n plus 1 is divisible by 6 for all odd integers n. We're going to start by proving our basis case, which is when n equals 1. So for our basis, we have 2 times 2 to the first plus 1 equals 2 times 3, which is 6. And that's divisible by 6, so that's true. Then we'll go to our induction case. So we'll start by assuming that it's true for our first odd number. So our first odd number is going to be 2k plus 1, and our second odd number is 2k plus 3. So we're going to assume that 2 times 2 to the 2k plus 1 is divisible by 6. So it's going to equal 6 times some number, we'll call it a, where a is some integer, 1, 2, 3, so on. So that's what we're assuming, and we're going to check that that's also true for 2 times 2 to the 2k plus 3 plus 1. So we'll try and make our 2 times 2 to the 2k plus 3 plus 1 look like our assumption. That way we can substitute something in and prove that it's equal. So we'll start by distributing this 2. So we have 2 times 2 to the 2k plus 3 plus 2 times 1, which is 2. So then we're going to split our 2 to the 2k plus 3 into 2 times 2 to the 2k plus 1, because that's what we have up here in our original one, and then times 2 to the second power, because 2k plus 1 and the squared exponent equal our 2k plus 3 in the exponent. So we have that plus 2. So then this becomes 2 times 2 to the 2k plus 1 times 2 squared, which is 4, plus 2. So now we want to rearrange our assumption so that we can plug it in. So we'll go over here. So we have 2 times 2 to the 2k plus 1 plus 1. So we're going to distribute that 2 in. So we have 2 times 2 to the 2k plus 1 plus 2 equals 6a. And then we'll subtract our 2 to get 2 times 2 to the 2k plus 1 equals 6a minus 2. So now we can plug that 6a minus 2 into here because they're both equal to 2 times 2 to the 2k plus 1. So we have 6a minus 2 times 4 plus 2. And we'll go over here to keep solving. So we'll distribute that 4 in. So we have 24a minus 8 plus 2. So this is 24a minus 6. We can factor out a 6. So we get 6 times 4a minus 1. So we have 6 times some integer, which means that our final answer is going to be divisible by 6. So we've proved that 2 times 2 to the n plus 1 is divisible by 6 for all odd integers n. So here we have our first IB practice question. This is a no calculator question. It says, use mathematical induction to prove that 1 squared plus 2 squared plus 3 squared plus ... plus n squared equals n times n plus 1 times 2n plus 1 over 6 for all positive integers n. So we'll start with our basis case. So for our basis case, we have 1 squared equals n, which is 1, times n plus 1, so 1 plus 1 times 2 times 1 plus 1 over 6. So our 1 squared is 1 equals 1 times 1 plus 1 is 2. 2 times 1 is 2 plus 1 is 3 over 6. So 1 equals 1 times 2 times 3 is 6 over 6. 1 equals 1. So this is true for our basis case. So now we'll do our induction. So for our induction, we'll start by assuming it's true for when n equals k. So 1 squared plus 2 squared plus 3 squared plus ... plus k squared equals k times k plus 1 times 2k plus 1 over 6. So we have 1 squared plus 2 squared plus 3 squared plus ... plus k squared plus k plus 1 squared, because we have an additional k plus 1 on this left side. So now we'll manipulate the left side to show that it's equal to the right side. So this here is going to equal our 1 squared plus 2 squared plus 3 squared plus ... plus k squared plus k plus 1 squared. So we separated this part and the k plus 1 squared. So we know this 1 squared plus 2 squared plus 3 squared plus ... plus k squared equals this from our first statement. So this is going to be equal to k times k plus 1 times 2k plus 1 over 6 plus our k plus 1 squared. So we need to create a common denominator by multiplying our second thing by 6 over 6. So we'll multiply this by 6 over 6. So this gives us k times k plus 1 times 2k plus 1 plus 6k plus 1 squared all over 6. So we can factor out a k plus 1. So we get k plus 1 times k times 2k plus 1 plus 6 times k plus 1 all over 6. And this k plus 1 is in parentheses. So we'll distribute the stuff on the inside. So this equals k plus 1 times 2k squared plus k plus 6k plus 6 all over 6. So then we can combine our like terms in here. So this equals k plus 1 times 2k squared plus 7k plus 6 all over 6. Our 2k squared plus 7k plus 6 can be factored. So we get k plus 1 times, this will factor to k plus 2 times 2k plus 3 all over 6. So we can rewrite this. We'll go this way all the way up to here to rewrite it because we've kind of run out of room. So we can rewrite this as k plus 1 times, this will be k plus 1 more times 2 times k plus 1 more all over 6. So we can see here this would be the n times n plus 1 times 2 times n plus 1 all over 6. So because it holds true for k plus 1, that means that it's going to be true for every positive integer n. So we've proved this here. So next we have our proof by contradiction. So it's typically given in the format of if A, then B. So this is like your if-then statement most of the time. So we start by assuming that the opposite is true. So if A, then not B. And we'll show that it's not possible for the opposite to be true. So if it's A, it cannot not be B. Therefore, it must be B. Once again, this will make more sense as we go through the examples. So for this practice problem, it says for all integers A, if a squared plus 3 is odd, then a is even. So for this, we have our A statement that a squared plus 3 is odd, and our B statement that a is even. So you could solve it by saying a is true and then proving that b is true, but with a proof by contradiction, you'll say that b is not true and then show how a can't be true then. So first we'll start by defining odd and even numbers. So an odd number is in the form of 2 times some integer plus 1, which makes it odd, and an even number is 2 times some number. So we're going to assume that a is odd. So we're assuming that our B statement is not true. So assume that a is odd. And we're going to prove that if a is odd, then our A statement, a squared plus 3, will not be odd. So it'll be even. So if a is odd, then a equals 2k plus 1, where k is any integer. So in a squared plus 3, we have 2k plus 1 squared plus 3. So 2k plus 1 squared is going to be 4k squared plus 4k plus 1. And then we have plus 3. So this is 4k squared plus 4k plus 4, which we can factor a 2 out. So we get 2 times 2k squared plus 2k plus 2. The reason we only factored 2 out is to prove that it's even. So we have 2 times some integer, which means that this is even. So if statement B is not true, so if not B, then statement A is also not true. Therefore, if statement B is true, then statement A will be true. So we have proved this. So now we have our second IB practice question. So it says use proof by contradiction to prove that the square root of 2 is irrational. So because we're using proof by contradiction, we're going to assume that the square root of 2 is rational. So if the square root of 2 is rational, then that means it equals some value a over b. And we're going to have a and b as whole numbers in simplest terms, so it can't be reduced anymore. So we'll start by squaring both sides. So we have 2 equals a squared over b squared. And then we'll multiply both sides by b squared. So we get 2b squared equals a squared. So because our fraction was in simplest form, that means that a and b can't both be even. Because if they were both even, then it could be simplified more. So a squared equals 2b squared. So 2 times some number b squared equals a squared. And because it's 2 times something, that means a squared is even. So anything squared is a number times itself, and an odd number times an odd number is always an odd number. So we know that a has to be even. So if a is even, then it's 2b squared equals some even number. So an even number is 2 times some number k. So we have 2k squared. So 2b squared equals 4k squared. And then if we divide both sides by 2, we get that b squared equals 2 times k squared. So this is 2 times some number. So we know that b squared is even, which means that b has to be even. So if a is even and b is even, then our a over b is not in its simplest term. So the square root of 2 is not rational, because it can't be written as a fraction with whole numbers in simplest terms. So here is how we prove that the square root of 2 is irrational. So finally, we'll have our proof by counterexample. So for this one, it's pretty straightforward. You show that a statement cannot be correct by simply providing an example that contradicts the statement. So for example, if someone said, if a food is a vegetable, then it's a carrot. We could disprove this by saying asparagus is a food and it's a vegetable, but it's not a carrot. Therefore, the statement is false. So we'll go ahead and do a practice problem with this. So for this practice problem, it says 3n squared plus 1 is always an even number for all values of n. So we could try plugging in different things for n. So if we plugged in 1 for n, 3 times 1 squared is 3, plus 1 is 4. So that's an even number, so that's true. Now if we plugged in 2 for n, 2 squared is 4 times 3 is 12, plus 1 is 13. So this is not an even number. So we could say, when you plug in 2 for n, 3n squared plus 1 equals 13, which is not even. Therefore, this statement is false. So we've disproved this. So now we have our third IB practice question with no calculator. It says disprove the following statement using a counterexample. 2 to the 3 power to the n power plus 3 is prime for every positive value of n. So we'll go ahead and plug in some values for n. So 2, 3 to the n plus 3. So we'll plug in 1. So when n equals 1, we have 2 cubed to the first power plus 1. So 3 to the first power is 3. 2 cubed is 8. 8 plus 3 is 11, which is prime. So now we'll try 2. When n equals 2, we have 2 cubed squared plus 3. So 3 squared is 9. 2 to the 9th is 512. Plus 3 is 515, which is divisible by 5. So we know that this is not true because it's not prime. And then you can end it just by writing disprove. So we've disproved this statement. So in summary, for proofs by mathematical induction, we prove the basis case, so where n equals 1, and then we prove our induction by assuming the statement is true when n equals k, and then using that assumption, we can show that the statement is true when n equals k plus 1. For a proof by contradiction, it's typically given in the format of if A, then B. So we assume that the opposite is true. So we assume if A is true, then not B. Or starting with not B, proving that A is not true. And then we show that it's not possible for it to be the opposite. So if A, it cannot be not B. Therefore, it must be B. For our proof by counterexample, we simply show that a statement cannot be correct by providing an example that contradicts the statement. That's all for this video. Thank you for watching.